This podcast is brought to you by LMU Munich.
Okay, so today is gauged supergravity. The last chapter. And keep in mind this sketch I was drawing yesterday. All the theories we have been studying so far in 4 dimensions, or much of the structure is quite generic and also holds in other space-time dimensions. All these theories are the ones obtained by torus reduction from 11 dimensions. And that's where all these big symmetry groups show up, the scalar coset model, the P-form couplings, and so on. And what we'll do today is switch on gauge couplings in these theories, so-called gauging. To find non-abelian gauge symmetry, to find fields charged under gauge symmetry, so everything you typically expect in a physical theory. If there's gauge symmetry, fields should be charged under it, minimal interactions, and in particular scalar potential. So here there's space for de Sitter solutions, anti-de Sitter solutions, masses of the fields, spontaneous symmetry breaking, and so on. All that comes only after introducing the gauge coupling constant. So there's a lot more structure in these theories, and that corresponds to the fact that it's that class of theories which typically you find if you do more complicated compactifications. Okay, but for the moment we will not at all look at this aspect of what could be the higher dimensional origin of such theories. We will just start from those supergravities we have been discussing. We will try to switch on gauge charges and see what is the most general deformation that we can switch on in these theories, which is compatible with supersymmetry. So here we are still talking about supergravity theories. Supersymmetry is valid. Good. So our starting point is the ungauged theory on the left. And let's just remind the symmetry structure of that theory. There was a global symmetry group, G, such that the scalar sector was a coset model G over K, such that fields transform in representations of this group, such that this is a symmetry at least of the equations of motion, if not even of the action. And for the maximal theories, these were the exceptional groups. But all this construction also applies to the cases where this is some other Lie group, as you saw or as we saw for the half maximal theories, and so on. So fields transform under this group. So for example, remember, I don't know, the scalar matrix transforms just by matrix multiplication. Okay. I think I had already introduced these indices. So alpha labels the generators of the algebra underlying that group. So we saw that the infinitesimal action on scalar fields is just by multiplication with the left matrix. This is the matrix, and that is the symmetry parameter, which contracts the matrix. We saw that, for example, on P-forms, say on a vector field, they transform in linear representations. So there would be, again, lambda alpha, a generator T alpha. Now in that particular representation, multiplying this vector, and so on. Okay. All the P-forms come in linear representations. That is the global symmetries. But then we also have local symmetries, of course. And I only talk about bosonic symmetries. We have local supersymmetry, that we know, that's somehow the starting point. But we also have local bosonic symmetry, local gauge symmetry. Because we have vector fields in the theory, massless vector fields, so they come with U1 gauge freedom. But as I said, the gauge groups you find here are typically abelian, and nothing is charged under these abelian groups. But still, it's a U1 gauge group. So there is a symmetry of the type A transforms as a gauge connection d mu of some lambda m. I use the same lambda, but of course it's a different object. It carries a different index. And this is a local symmetry, and it's just a partial derivative because it's an abelian gauge group. So this would be some, say, U1 to the number of vector fields gauge symmetry. Okay? So we have global symmetry, which is non-abelian in general, some exceptional groups. We have local symmetry corresponding to the vector fields, and that is abelian. So how do we introduce non-abelian gauge symmetry? Well, that's a standard procedure, which you have seen presumably when you did Young-Mills theory. Yes? Yes?
In the second transformation, delta lambda of A mu m.
Yes?
Should there be an index alpha also at the lambda on the left-hand side? Or there is no symmetry?
Oh. Well, I mean, this is more schematic. Lambda for me is just an algebra element, and I can expand it, say, in the basis of generators.
But in the first equation, there is a summation over alpha.
Here there's summation over alpha. Here there's also summation over alpha. Right? This is nothing but, say, I could call all this guy a lambda, which is a matrix in that representation. And all I've done here is, again, I do that because later on it will be useful to have these explicit generators to work with. Okay? But there's nothing subtle in these equations. Okay? So the way we can introduce non-abelian but local symmetry is by getting these two symmetries together, and that's what is called gauging. So what does it mean? We pick a subgroup G0 of the global symmetry group. This was global, this is also a global symmetry group, and we turn it into a local gauge symmetry. So we promote it to local gauge symmetry. So let's do that on the level of the algebra. We pick gauge generators and how many can we pick? Well, as many in principle as we have vector fields. Right? We have a fixed number of vector fields. We can certainly not obtain a gauge group which has a dimension larger than our number of vector fields, which we have. at our disposal. So we can introduce gauge generators, as many as we have vector fields. Let's call them xm. And well, they must be selected among the generators of G. Right? These are linear combinations of the generators of G. So linear combination, I put some matrix of coefficients, then again sum over alpha. So it's a subset, it's a linear combination of these generators, and then I pick a number of such linear combinations, and that's the generators of my new gauge group, G0. Okay. And so the whole definition of what is the new gauge group, which we're going to introduce, sits inside of this matrix, theta m alpha. Okay. That matrix is what is usually called the embedding tensor, because it tells us how this new gauge group really sits inside of the old global symmetry. And once we have picked these generators, well, we can use our vector fields to make this into a local gauge symmetry. And that's just the same way as it works for Young-Mills. We can covariantize our derivatives, introduce minimal couplings, and then by construction, our theory acquires a new local gauge symmetry. So introduce minimal couplings. As follows, covariant derivative, now defined as d mu, minus, let me put a gauge coupling constant here, connection a mu, vector field m, contracting the gauge generator. Okay, and let me spell it out. So there's theta m alpha, and then t alpha. Okay, so we have taken a subset of generators, we have coupled them to the vector fields, and thereby made them into local gauge symmetry. That's kind of that's all. Now it looks a bit different than what we have been used to in, say, Young-Mills theory. In Young-Mills theory, you wouldn't do all this kind of pre-discussion of what is my global symmetry, what are my vector fields. If you want to construct Young-Mills theory, non-abelian gauge theory, typically you just start from a model which has a given global symmetry. You just start from, say, fermions which have global SU3, and then you introduce 8 vector fields, because that's the adjoint representation of SU3. We need 8 vector fields to gauge SU3. We couple them and everything works out. The thing is, in supergravity, we are much more constrained because, first of all, we cannot just invent some global symmetry, but the global symmetry is already there. It's given to us, and it is some particular choice of groups. So we cannot gauge an arbitrary group. We have to live with subgroups of these groups. Okay, we're not free. And moreover, even for a given subgroup in here, in general, we cannot kind of introduce sufficient number of vector fields as we like, because vector fields are not to be introduced. They are also already there. Remember, we're doing supersymmetry. The number of vector fields you can see in the tables of multiplets, right? The vector fields are already in the theory. In general, I'm not allowed to add extra vector fields that will spoil the counting of degrees of freedom. So I have more constraints to satisfy. I have a global symmetry group which is given. I have a number of vector fields which is given. And so all I can do is I should try to use these vector fields to gauge subgroups of this group. And that's why this funny matrix theta m alpha appears. In Young-Mills theory, typically you would just introduce as many vector fields as you wish, and this theta would just be basically delta. You pick a number of generators, you add as many vector fields, and then everything goes through. Here we have to use the elements which we are given, fixed set of vector fields, which have already certain properties like their transformation behavior. A given global symmetry, and all we can do is tie them together. Okay? That is what gives more constraints on this construction than in arbitrary Young-Mills theory. Well, on the other hand, this is as good as we can do. If we introduce these minimal couplings, we will have local gauge symmetry by construction. And sort of the whole structure, the entire structure is encoded in the choice of this matrix. Okay, that matrix knows everything about which are our gauge generators and how are they coupled to the vector fields. So it's completely encoded. The structure is encoded in this matrix. So that sort of parameterizes our freedom of what are the theories which we can construct. And as you see immediately, I will not be allowed to put an arbitrary matrix here, right? This is a rectangular matrix. It has two indices of different sizes. But of course, if I put just arbitrary entries into this matrix, in general, the whole construction will be inconsistent. So theta must satisfy a number of constraints. For example, whatever we do, whatever gauge theory we find, these generators we pick, they should close into subalgebra. Okay, if these are like an open set and by commuting two of them I go beyond the set of generators, well, that will not be a consistent choice. So somehow in the choice of this theta must be encoded the fact that we are defining a subalgebra here, not just an arbitrary subset of generators. Okay. So for example, this set of all xm's should be a subalgebra. Okay, but let's be more systematic. In fact, one can very nicely describe what are the constraints which this matrix should satisfy. And it will just be algebraic constraints on a given algebraic object, which is this matrix. And there's two types of constraints which you typically find. So there is the quadratic constraints, quadratic because they are bilinear in theta. They are very easy to understand why they are there, but typically they are not so easy to solve, as we will see. So what is the quadratic constraint? Well, theta has two different indices, one in the adjoint of G and one in the fundamental of G. But as you can imagine, theta in general is not, of course, an invariant tensor of G. Okay, no group has an invariant tensor between with two different indices. That could only happen if this M is in the adjoint representation as well. So in general, this is not a tensor which is invariant under the action of G. Okay. But there's no need to have that, because presumably in this process of gauging we will anyhow break that former global symmetry. All that matters is that we still have local G0. Okay. But to have everything consistent, theta should certainly be an invariant tensor of G0. It's like the set of coupling constants which we introduce. So a Lagrangian, which has local G0, also has global G0. So whatever object or tensor I introduce, it should be an invariant tensor of G0. Right? So theta must be a G0 invariant object. Like when you write down non-abelian gauge theory, what you use is the structure constants of the gauge group, and the structure constants by definition are invariant tensors of the algebra. Okay. Now, can we make this more specific? Yes, let's just see how would theta transform under G? How would theta transform, say, under G? Well, there's an action on these two indices. There's an action on the lower index m and an action on the upper index alpha. Well, on this index it would transform by precisely that representation matrix we were introducing. Okay, linear action on that vector. And on the upper vector, well, it would transform exactly the same way, just with a different representation matrix, namely the representation matrix in the adjoint representation. And what is that? That is the structure constant of the group. So it will be plus lambda beta. Now my generator is the structure constant of the group, theta m gamma. And in general, this will not be 0. Precisely because theta is not a G-invariant tensor. But it should be 0 if I do a G0 transformation. So, but should vanish for a G0 transformation. Now, what is a G0 transformation? Well, that's a transformation by X. So in some sense by the projected, not by an arbitrary T alpha generator, but by this projected set of generators. That action should vanish. Well, that we can spell out. So we simply project this variation with another theta. So we get theta m, well, yet a different k, say, k beta. And now we simply copy what is written up there times T beta m n theta n alpha plus f beta gamma alpha theta m gamma. So that must be 0. Okay, so the condition that if I act with the gauge group generator on theta, theta is invariant under that action. And you see this gives a simple algebraic equation for theta, a quadratic equation for theta. So that's a bilinear equation. And we will refer to that as, say, the quadratic constraint. That equation may look a little kind of abstract or not so intuitive, but in fact, it takes a much simpler form, much more intuitive form. If I multiply it, if I contract it out with a generator, multiply with a generator T alpha, because if I do that, you will see that here basically I have two generators, and here I have a structure constant, again multiplying the generator, which is a commutator. So if you multiply with that generator, the equation you find is the following. xm commutator with xn is minus xm nk xk. So from here you get a commutator, and from here you simply get this combination xmnk times the generator xk. Now that looks much more like an algebra. Just to be, so what is this guy? xmnk, just to be precise, xmnk is the generator xm in the representation nk. So what is that? Well, remember the definition of our generators. This is theta m alpha t alpha nk. So again, that's something you can compute in terms of this new matrix theta and the old generators of the algebra. Okay. And then this condition here shows that if you commute two of the generators, the result again is proportional, is a linear combination of generators with a particular, say, structure constants, and these structure constants are those guys. Okay? So in particular, we see that this kind of abstract discussion tells us that the gauge algebra closes. And in some sense, this quadratic constraint you can understand morally like a Jacobi identity. Okay? It's like a generalized Jacobi identity. We'll see in a second why it's generalized. So as usual, when you write down an algebra, in order to have a consistent algebra, which is associative, you need the structure constants to satisfy some bilinear identities. Those are the Jacobi identities. And this corresponds precisely to that equation, or to that one, if you rewrite it.
Could you get the same conclusion by starting from our gauge theory should be closed?
Good question. We'll see that in a second. This turns out to be stronger than just imposing closure of the gauge algebra. If I had just imposed closure of the algebra, I will in general find a weaker constraint, and that is not sufficient for consistency. In some sense, it should not only be closed, but it should be closed with the particular properties of the structure constants. So this is really a necessary constraint to impose, this G0 invariance, and as a consequence it has closure, so we are fine. Okay, but closure alone would not have been sufficient. So that's the quadratic constraint. It's easy to understand where it comes from, morally, but you find some equation which in general you can imagine is hard to solve. Right? Try to find solutions to these equations. It's as if one gives you the Jacobi identities and one asks, find all the solutions to the Jacobi identity. And if you didn't hear about Lie algebra theory and Dynkin classification of algebras, just looking at the Jacobi identities, it's very hard to see what are the possible solutions of that set of equations. Okay? So here it's a bit more general because these are not Jacobi identities, it's slightly more complicated equations. In particular, they carry the structure constant and generators of some big group G, not the gauge group, but some underlying global group G. So some G covariant equations. And depending on the choice of G, this equation may have very different sets of solutions. Okay, that's one class of constraint, but in general there's a second type of constraints which this theta has to satisfy. Okay, yeah, let me first say the second set of constraints, so-called linear constraints. So those are equations which are linear in theta. Well, equations linear in theta typically are very easy to solve. But these equations are slightly harder to motivate. Roughly, you could say this is a constraint which comes from supersymmetry. Imposes linear constraints. Remember, for the moment, we're just looking at local gauge symmetry. We have some global symmetry to start with. We want to make it into local gauge symmetry, and we do that by our standard Young-Mills construction. But the theory we started from had some additional property. It was supersymmetric. There was a supersymmetric extension with coupling to fermions and all that. All this we have totally neglected for the moment. So you can imagine that if you start introducing now any non-abelian gauge symmetry, maybe it's totally consistent as a non-abelian gauge structure, but it could easily break supersymmetry. Okay. Supersymmetry may be selective about what are the possible groups which we can gauge. And indeed, if you try to make all this into a supersymmetric theory, you will find that, well, introducing minimal couplings gives new contributions to a supersymmetry variation. In general, supersymmetry is broken. We need to do some kind of Noether procedure, add additional couplings which compensate, and so on. And it turns out we can do that only for very particular choice of theta, not for every theta. And that is, but it can be nicely rephrased as just linear constraints on theta. In some sense, it's like doing a deformation of our Lagrangian. You see, this theta is really the object which deforms the Lagrangian. We introduced couplings, everything proportional to theta. So you could think of the first non-trivial check of supersymmetry will be some equation linear in theta, linear in that deformation parameters. And that is true. And that will give you some linear constraint on this theta. Now, this linear constraint is less, in some sense, less universal than this quadratic constraint. The quadratic discussion we could do without saying what is the group, what is the matter content, and so on. It turns out this linear constraint is really more specific to the choice of group G and the representation in which the vector fields live. So let me just start by some example, the prime example of what we are always discussing. Prime example would be four-dimensional maximal supergravity. And recall the numbers. We have a global symmetry group, which was E7. So its dimension is 133. And we have, if we combine electric and magnetic vector fields, we have 56 vector fields AM transforming the fundamental representation of E7. So the index alpha here would run from 1 to 133. The index M runs from 1 to 56. So theta M alpha, it's a matrix 56 times 133, rectangular matrix, pretty big. Now, which type of constraints can we expect on such a matrix? Well, number of components is this product, but it's not just a product of numbers. These are representations of E6. That's the fundamental, that's the adjoint representation. Okay? A product of representations, in general, splits into different irreducible pieces again. And turns out if you do that for E7, you look it up in the tables, the product of the adjoint and the fundamental representation has 3 irreducible pieces. There's a 56. Again, well, that makes sense because we multiply the adjoint to something. There is a piece which lives in the 912. And there's a third piece which is much bigger, which lives in 6400. and 80. And now you can already imagine if we are to find some linear constraint on this matrix, and since all we are doing is really G covariant, in this case E7 covariant, it's natural to expect that if one parameter in here does the job and is consistent with the supersymmetry, then presumably the whole representation will be consistent with the supersymmetry, because everything is E7 covariant. So in a representation, one component is as good as all the others. So we can expect that whatever we find as a condition, in fact, will not be a very complicated condition on the entries of that matrix, but will simply be a condition on these three blocks which we find here. Okay? And that is indeed the case. So if you study supersymmetry, just to lowest order in everything, lowest order in the fermions, lowest order in theta, you will find that supersymmetry immediately rules out these big representations. So none of these parameters here is good, and same for the small one. None of these parameters here is good for supersymmetry. And supersymmetry selects just the middle block, 912 parameters. Okay, that's still quite a lot, but far less than what we started from. So this is a big matrix, and it has 912 independent components.
I have a question. If I want to only gauge some of these symmetries, it seems like because the 56 vector fields are connected by the duality, it seems like I can choose arbitrarily and to gauge any number of symmetries I want.
That's right. That's right. In fact, we will recover that as a corollary of what we're doing. But yeah, it's a good remark. Yeah. In some sense, in 4 dimensions, that's special. The number 56 is a bit fake, because we had originally only 28 vectors to start from. But we will see that, in fact, this structure simply will precisely give us back that condition. And that's specific to 4 dimensions. In higher dimensions, 5, for example, typically you could think of really using all the vector fields that you have at your disposal. And this algebraic structure goes through in all dimensions. And the nice thing is, if you happen to be in some dimension which has some special property like 4 dimensions, then this precise procedure gives you all the constraints which are necessary for 4 dimensions. Okay? So if you do this, you don't have to worry about what is in which space-time we are living, what are the properties, what could be gauged, what could not be gauged. All this will come out of the procedure. We will see that. So that's a linear constraint. That's very easy to solve, right? This is just like looking at projections on, well, I mean, you should do some numerics, or I don't know how to do that, but it's big matrices, but morally it's very easy to solve. It's a linear equation, just like computing projectors on irreducible representations, like Clebsch-Gordon decomposition. Good. So this is the linear condition. And now the statement is, and in different dimensions it will look a bit different because the group is different, the number of vector fields is different, there's different tensor products showing up and so on, but the structure will always be of that type. There will be some piece surviving the constraints from supersymmetry. And the statement will be, if you have a solution to the linear and quadratic constraint, that gives you a consistent supersymmetric theory. That is quite strong. Because this is a constraint which you pick at lowest order in that deformation and at lowest order in the fermions. Okay? If you're unlucky, it could happen that in higher order of the deformation or in higher order in the fermions, you might still hit another constraint. And if you're unlucky, that might also kill these 912 parameters. But that's not the case. Turns out once you have satisfied this and you have satisfied this, The construction works to all orders, and you can do this Noether procedure, and it will stop after a finite number of steps and give you a totally supersymmetric Lagrangian. So, for example, one way to go is, this is easy to solve. So we can we can spell out this big matrix, now parameterized by 912 independent parameters. So you have a big matrix, you have 912 variables inside. And now this matrix you plug into this quadratic equation. And then you get a big number of quadratic equations. If you do this for this theory, this will be about 8,000 quadratic equations. So you have 8,000 quadratic equations for 912 parameters, and you should look for solutions. And you can imagine there are, in general, not very many. Because not only do we want solutions, but also we want real solutions. Right? These coupling constants, we want them to be real, because we're just talking about real structures here. So in fact, maybe that I should mention here, we want real solutions of this. And you know, if you're unlucky, a quadratic equation can have not a single real solution. And here it's like a huge number of them. So solutions will be really rare. Okay? But the nice thing is there are still many non-trivial solutions to these equations in general. And they correspond to many different gauge groups which you can find, but still it's a highly selective construction. Supersymmetry in the end is highly selective. Let me make one remark. Coming back to your question in the four-dimensional theory. In 4 dimensions and maximal supergravity, the quadratic constraint, this is its generic form, which applies to any theory. In 4 dimensions, this can be written in a much simpler form. Just the following. I take a theta m alpha. Well, it's a bilinear condition, so there should be at least 2 of them. Well, there should be precisely 2 of them. And I contract them with omega mn. Omega mn being the symplectic matrix 0, 1, minus 1, 0, which happens to be an invariant tensor of E7. E7, in fact, is a subgroup of SP56. So this is a tensor, a group tensor. This contraction should be 0. That's all. That's not obvious at all. Okay. Why this equation takes that simple form, why the structure constants go away, these generators go away, and so on. You can really encode in that form. It's related to the fact that theta also satisfies this linear condition. This only is true if theta is a supersymmetric solution. Okay. But this is an equation which is much easier to deal with. And it tells you immediately some nice properties. Like, I mean, what does it mean? As a matrix, this means matrix times itself transposes 0. That can only happen if the matrix has at most half maximal rank. So the rank of this guy is at most 28. And that fits nicely because we know that in 4 dimensions we had in the beginning only 28 vector fields to start with. We added the magnetic duals to make this into a single representation. Okay? But now the constraints tell us back we are only allowed to use 28 of them. Although that may not have to be the 28 original vector fields. All we are told here is, among that set of 28 electric and 28 magnetic vectors, choose some up to 28 gauge vectors which we use for the gauge group. Okay. But the nice thing is, those could be like a subset of formally electric and formally magnetic vectors, which we could use to gauge. And that perfectly works through in this form.
In the D7 exception field theory, is this related to the section condition? It has the same intriguing form.
Well, that's one of the open questions. Well, you see, when you think about the section condition, in that particular case in 4 dimensions, there are 2 section conditions. It's not just contracting with the omega, but also projecting with the generator. And there's no analog to that equation. So if I contract these 2 with a generator, T alpha, T gamma, say Mn, in general this is not 0. Okay? And so the most naive idea that this would just precisely descend from the section condition by making the proper ansatz cannot be that easy. But it's related to the fact that we don't really know exactly how these theories sit in in those exceptional and double field theories. And so we cannot. But of course, morally that's the idea. What you have as a section condition in those theories should sort of boil down with a particular ansatz to what is this quadratic condition for the embedding tensor. Yes. Other questions? And let me not. Okay. It looks like a very nice structure. So it allows you to really say in very few lines, characterize those thetas which are good supersymmetric deformations. Of course, then most of the work is in really doing that deformation and making sure that everything works out with the supersymmetry. And that, of course, we cannot do in much detail. And also you should do that in every dimension, of course, separately, because spinors look differently and the whole supersymmetric structure changes a bit. But there are a few general things which we can discuss. To see that everything is consistent, or how everything can be made consistent. Just in the bosonic sector. There's in particular one thing which I have sort of not, which for the moment I have a bit hidden under the carpet. That's the, let's call that chapter 2, the deformed gauge algebra. And that leads to some important property of these theories. Namely, let's go back to this quadratic condition which we found, but I don't write it again. Commutator of 2 generators gives this type of structure constant. Well, maybe I write it again. The commutator of 2 generators gives this type of structure constant. So that's very good for closure. And it looks almost like a standard Lie algebra. But that is kind of a fake observation. If this were a Lie algebra, then this should be the structure constant. And the structure constant, as you know, is antisymmetric in the two lower indices, because on the left-hand side there's a commutator. But now look at the definition of this structure constant. It's written up there. Well, it's some combination of this theta matrix, the embedding tensor, with the generators. And just from the very construction, you see there's no reason why this should be antisymmetric in the two indices. And in fact, in almost all cases, it's not. Okay? So this is a guy which has some symmetric part in its two indices. And we could parameterize it, for example, by something which I call a structure constant, antisymmetric in these two indices, but then also a, in general, symmetric contribution in general. And as I said, this is almost never zero. Well, that looks weird because, I mean, the left-hand side is clearly antisymmetric in Mn. It's a commutator. How comes the right-hand side is not? Well, it just means we are looking at two equations here. If I project everything to its antisymmetric part, I will find the structure constant here, Vf. But if I project everything to its symmetric part, or say consequence, if I project this to its symmetric part, it drops out. So there will be just this symmetric contribution multiplying x should be 0. So zk mn is orthogonal to x. But that in itself is not really an inconsistency. It just means, well, not all the x's are independent. That is to be expected. We have a big number of vector fields. Here we made some formal construction introducing as many generators as we had vector fields, because that's a maximal number. But in general, this theta matrix will not have a maximal rank. And here we saw explicitly, for example, in that case, it has at most half maximal rank. So among these generators, there are many kind of combinations which are 0. And here is a number of them. Okay? Well, so what's the problem? Well, the problem is, still the defining algebra was this. My structure constant, if I define it as the antisymmetric part of this x, these guys, now they are properly antisymmetric, but they will not satisfy the Jacobi identities. The guy which satisfies the Jacobi identities is x. Right? This is like a Jacobi identity for x. So you have the choice, either you project on something which is antisymmetric, or you stick with something which satisfies the Jacobi identities, but you cannot have both. Okay. It's a simple calculation. Just plug in this expression for x upstairs, and you will get something which looks almost like Jacobi, but it's non-zero. Okay. So in turn, does not satisfy Jacobi. But rather, well, I could spell out that relation, why not? F mn q. So if I have something which looks like Jacobi plus well, cyclic, the two other terms, you will find something proportional precisely to that tensor Z QMX or F minus NK Q. Okay? So Z is the device which measures how much X is non-symmetric and how much F does not satisfy Jacobi. Okay, it goes together. You choose, but you cannot have both. Well, still you could say who cares, because we have this is certainly an algebra, so there's some consistent structure underlying this. If F doesn't satisfy Jacobi, let's go with X, and that will satisfy, that will be a consistent structure. The problem comes because if we do non-abelian gauge theory, we need Young-Mills field strength. And what is the Young-Mills field strength? Well, of course you know that formula, but you know it for the case of the Lie algebra. Say minus or plus, whatever my conventions are, minus. Well, and now that's the thing. What should I put here? It will be A mu K A nu L. And if you were in Young-Mills, well, you would contract these out with a structure constant. That's a non-abelian part. Right. But now this F doesn't satisfy Jacobi, so should we maybe use X? Well, we can't really, because this is antisymmetric in mu nu, so it's antisymmetric here. So whatever this Z is will just drop out from the field strength. Okay. So for the field strength, we have no choice. The field strength is defined in terms of this F. That's the best we can do. But since this F does not satisfy Jacobi, well, this field strength will not be a covariant object. At some point, you will have calculated that under gauge transformations, the non-abelian Young-Mills field strength, in fact, transforms covariantly like a vector. That's the whole point of this definition of the extra term. But if you think about it, in the course of that calculation, at some point, you make use of the Jacobi identities for F. And if the Jacobi identities don't hold, well, then this is not covariant. And you can be very specific. You go through the calculation, and it tells you this F is a covariant object. Almost. Well, it has the right term to start from. Say, under a lambda gauge transformation, it goes in the right form. This is what would be a covariant transformation, just a rotation with a generator x. Okay. But there's some extra term, again measured by z. Sort of the thing which tells you how far you're away from Jacobi, and it looks like this: F mu nu L minus AK mu delta A nu L. Okay, so all this thing is non-covariant. Now that's a problem, because at some point we will be obliged to write some kinetic term for these vectors. And we know what this kinetic term used to be before we did the gauging, because before we switched on the gauge coupling constant, well, we had a kinetic term which was more or less like this. F mu nu m, F mu nu n. And the whole point of G invariance was the fact that F transformed like a vector, and this also transforms by matrix multiplication, so this whole thing is invariant. But now it seems that under gauge transformations, this Maxwell term or Young-Mills term will no longer be invariant. Because the transformation of M doesn't change. That's just about transformation of scalars. But the transformation of these field strength acquires that extra term. Okay, so that's this would not be gauge invariant. Now that's a disaster. We were fine with a minimal coupling, so we could make the scalar sector, for example, gauge invariant. The fermionic sector, we can make it gauge invariant by putting all the right minimal derivatives. But now it turns out for the field strength, the object, something like a covariant derivative on the vector, morally speaking, that guy is not gauge invariant. So what can we do? Well, there's a nice solution to that, which at first looks a bit brutal. Okay, but it turns out it's exactly the thing to do, and it describes everything for you. And it describes exactly what you find then from dimensional reduction and so on. We need a modified, a covariant field strength, which really is the good object to replace F on the level of the Lagrangian. And that will be the following. Let me call it curly F. Well, it will not be too radical. It will certainly contain a piece which looks like the Young-Mills field strength. But now how do we make sense of this extra term? Well, it's an extra term, but it's not totally arbitrary. It comes under projection of this Z tensor, the Z tensor which measures how much Jacobi is violated. Okay. So we will correct this field strength also by a term projected with that same tensor. Well, and now what should I put here? I'll put a new field B, a two-form, carrying two indices, KL, and being symmetric in these two indices. Now that, first of all, looks a bit brutal, because where does all of a sudden the two-form come from and so on? Let's worry about that in a second. But once I do a correction of that type, it's clear I can make all this into a covariant object if simply I postulate that B transforms such that it absorbs all this extra term. Moreover, this is not a totally weird coupling. This is like a Stückelberg type coupling of a two-form to a vector field. So all this will be covariant under the following transformations: d alpha, d beta. Covariant derivative of its parameter. And here we need to subtract that contribution. Say again? Oh, new, yeah. Sorry, it's a two-form, of course, thanks. Lambda k fl mu nu, then plus. I don't know why there's a factor 2. Maybe I'm off by a factor or something, don't worry about that. Then plus a k mu delta a nu L. But it's a two form, in fact, the two form, as we have seen, comes typically with its own gauge transformation, with its own gauge freedom. And indeed, there will be some new gauge symmetry which comes with it, which is just twice covariant derivative of, say, a new gauge parameter, lambda KL, which is a one-form gauge parameter, and it's like the standard tensor gauge transformation, however covariantized, in the sense that we have covariantized all our theory. And now what happens is that also the vector fields turn out to transform under exactly this tensor gauge transformation. Okay. So what we end up with is like a coupled system. We have vectors and we have two forms. They combine. Both are massless, both have their own gauge freedom. So this has gauge freedom with parameter lambda m. This has gauge freedom with parameter lambda KL. And we can define a covariant field strength and so on. And then in principle the story goes on. Now we have introduced a two form, so we should also define its field strength, which will be a three-form field strength. In general, that guy will not be covariant. We need to make it covariant. We need to introduce yet another form, which will be a three-form, and so on. Okay. Continues. We will have to introduce a three-form, which couples to the two-form, a four-form, and so on. It's like a whole hierarchy of P-forms. But in principle, all that is not so surprising. It's really a very neat structure. You see, already the variation of the scalar fields in the gauge theory, they transform under gauge transformations, and they basically transform with a lambda parameter. I just do it schematically here. They transform with a lambda parameter of the vectors. So it's not so surprising that the vectors will also have some transformation with a gauge parameter of the two forms. And the two forms will have their gauge transformations, but once we introduce three forms, these guys will also transform, now with the gauge parameter of the three forms, and so on. In some sense, the moment you start doing gauge theory on this, gauging the scalar fields, it's pretty natural that also the vectors start transforming under higher P-form transformations. That's exactly what happens. Hierarchy. Well, so now let's go back and worry. Yes?
Can't we truncate this by just making some P-form like constant field, like not constant, but non-propagating?
Non-propagating.
Yeah.
That is exactly what will happen. And again, this is exactly what will happen almost by itself. For example, in 4 dimensions, what we will see is, well, there is this need for the two forms. So we will need, I'll say a bit about that, we will have to introduce two forms to the Lagrangian. But the only way we can do so, I mean, we don't want to introduce new degrees of freedom. The only way we can do so is by introducing it as a topological form. So the two form will come with some BF coupling and will just be a topological form in 4 dimensions. It will not introduce extra degrees of freedom. And the three form, which we see here showing up if I do this hierarchy, the three form will not even show up in the Lagrangian. in 4 dimensions. It will be projected out, as you say, but that will happen all by itself. So now, but still, even if these are, so the 2 forms should not introduce new degrees of freedom. B mu nu should not introduce new degrees of freedom. Well, one way to achieve that is by coupling them in a topological way. But that is possible in 4 dimensions, in higher dimensions. There's no way to introduce 2 forms, for example, as just topological fields. So the only way this can work is if the 2 forms are the 2 forms which are already in the theory. So in some sense, they should already be in the theory. And let me give you one example to say what I mean by that. In 4 dimensions, and that is generic, in 4 dimensions, in fact, the linear constraint on theta can be understood in a very generic way. Can be rephrased in the following way. Define x. Well, we have xm and k being this combination of generators. Define the 3-index tensor. Bring the index k down using that symplectic matrix, which is always there in 4 dimensions. Then this guy, by definition, is symmetric in the last 2 indices. Since all the groups are subgroups of some symplectic, not n, say k, group in 4 dimensions. So this object is a matrix which is symmetric in its latter 2 indices. And the linear constraint tells you, it's like a symmetry condition. It tells you if I symmetrize in all 3 indices, this guy should be 0. That holds for all groups, for all number of supersymmetries, and so on. Okay, the linear constraint wants x, the totally symmetric part in x, to be 0. And why is that useful? Well, look at the field strength. The new field strength, which used to be the old one, plus this extra bit. under projection with Z. But what is this thing? Well, Z just used to be the symmetric part in X. Z is the symmetric part in X, which measures how far I'm away from antisymmetry. So this is nothing but X symmetric in KL M BKL. Okay. But that's nothing but, well, let's bring this index down. It's this combination of x's. Now we know x by definition is symmetric in the last two indices. Here I project onto the first. Moreover, I know that the totally symmetric x is 0. Now if the totally symmetric x is 0, it means I can shuffle this index over here, just using the fact that the totally symmetric part is 0. This becomes minus 1/2 omega mn xn KL BKL. This is due to the linear constraint. And now what's that? Well, this is minus 1/2. Let's split this up again into the embedding tensor multiplying the generator. So this is the embedding tensor, lifted one index, m alpha, and then a generator T alpha KL BKL. That's all. We have just rewritten that combination. But what do we see? We see that BKL does not appear like a free object with KL indices free. It appears under projection with a generator. It's only this combination which we need actually. Okay? As here we could have said that it's not BKL which we need only the projection with a Z. But Z is an abstract thing. Z may depend on what gauging we have chosen, what theta is and so on. Here we don't see very much. This is independent of what gauging I have chosen because the gauging is encoded here. Whatever gauging I choose, all I need is not two index forms, I need just adjoint two forms. And that makes perfect sense because remember, in 4 dimensions, two forms are dual to scalar fields. Two forms are dual to zero forms. Zero forms are scalar fields. 2 dimensions, two forms are dual to scalars. But scalars parameterize this coset space. So we naturally can define as many two forms as our group has a dimension. We can define two forms in the adjoint representation of the symmetry group of the theory. Okay? So we can define, say, dim G two forms. And those are precisely the ones we need to correct the field strength. So in 4 dimensions, it turns out we have not really introduced a new object. We have introduced an object, which is an object which was in fact already there. It was just the two form which was dual to the scalar fields. And simply in the original theory, in the Lagrangian, we don't see it, we don't need it. Because all these dualities are on-shell dualities. But once you have your equations of motion, you could, if you insisted, you could define that number of two forms. And they are perfectly consistent, for example, with the supersymmetry for that reason. You have field equations of a supersymmetric theory which allow you to introduce these things. So there is a consistent supersymmetry law for this number of two forms. It's much harder to write down something for this. We don't know if that could work in general. But for this subset, certainly can work, and we can write consistent supersymmetry transformation laws. And that's why everything is consistent. And it works exactly in the same way in all the higher dimensions. It's always the special properties of this tensor Z which makes sure that this B is not just an arbitrary thing we have introduced desperately to make this work. But this B in all cases turns out exactly the B which is in the theory. If you look in the table in higher dimensions, usually there are already two forms in your theory. In 6 and 7 dimensions, two forms sit in the supergravity multiplet. And the whole construction goes through, and this very construction tells you the B you need to put here. Of course, for that you will have to work out what is the form of Z, what is the form of theta, and so on. But if you plug in all that, it turns out the two form you need to make it work is exactly the dynamical two form you had in your theory. And maybe just to finish, let me sketch in like 2 lines which I have left. Now what happens to the Lagrangian if we switch on the coupling constant? So the Lagrangian has basically has 3 modifications. First of all, we covariantize what used to be the ungauged Lagrangian. Well, what does it mean? Standard covariantization. We introduce minimal couplings, as we discussed. But, for example, we should also covariantize field strength for vector fields and field strength for higher rank tensors. In that way, we have been discussing not just introducing the Young-Mills coupling, but also introducing all these trickle-type couplings to higher forms. Only then this Lagrangian will be gauge invariant. It will be gauge invariant, but supersymmetry in general will be broken because we have introduced minimal couplings. There's additional contributions to supersymmetry. It will be broken, and to restore it, we need to add additional Yukawa-type terms bilinear in the fermions with scalar matrices, which depend on the scalar fields. So very schematically, tensors like that, whatever type of fermions you have in the theory. That restores supersymmetry at the lowest order in the coupling constant. It spoils supersymmetry at next order in the coupling constant. In order to cure that, you need also to introduce a scalar potential. And that will be a function of the scalar field. And if you did this small exercise on the ADS supergravity, supersymmetry of an ADS extension in 4 dimensions, morally, it's exactly that type of calculation. You introduce some kind of modification of the covariant derivatives. In that case, it was just by a shift in the variation of the gravitino. You need a mass-like term for the fermions, in that case for the gravitino, to compensate for that. But supersymmetry will be spoiled unless you add yet another term, which is the scalar potential. In that case, it was just a cosmological constant. So these guys, these mass tensors, they will be proportional to theta. That is to the coupling constant. Okay, so they will be functions of the embedding tensor. The scalar potential, already as an ADS supergravity, will come in quadratic order in the coupling constant. So here it will be quadratic in this matrix theta. And just the very last formula I can still put is again coming back to our prime example, which is 4-dimensional maximal supergravity. Of course, I cannot introduce any of these spinorial structures, but at least I can write out the scalar potential, which takes a quite compact form. And we can give it for any choice of gauge group. And it's a pretty compact form. it should be bilinear in this, matrix theta, and I'll give it in terms of this matrix X, which is a theta contracted with a generator, R, X, PQS. So those are just constants. Those are like this generalized structure constants, and they are contracted out with a scalar symmetric matrix we have introduced, which describes the coset space M and Q. And there's a second term, factor 7, which is kind of specific for this theory. Q, X, and QP, M, MN. Okay, so you see the final formula after going through all the supersymmetry calculation, which we haven't even done in detail. The final formula for the scalar potential is rather compact. It's quadratic in theta, so it will be quadratic in this coupling constant. The scalar dependence sits inside of these matrices M. So for a given gauge group, for example, the main example would be gauge group SO8, subgroup of E7, corresponding to 11 dimensions, compactified on a 7 sphere. Well, you choose the corresponding theta, which goes with it. From that, we calculate X, contracting it with a generator. You plug it in here, and you have the scalar potential as a function of 70 scalars. Of course, it's a very complicated function. You would have to parameterize this matrix in some way, and this will be complicated object, but the very definition is very simple. Okay? And it holds not only for this theory, but you choose any other gauge group inside E7, compatible with all the constraints we have worked out. And the formula for the potential is exactly the same. So you can go the other way. You can try to shape this potential. I mean, these are the parameters which shape the potential, such that you have certain properties which you want to discover. And that will tell you which is the gauging which you have to switch on in order to recover that structure. Okay, so at least that, in some sense, is a good point to finish. We have more or less the basic ingredients of constructing a gauged supergravity Lagrangian, which is supersymmetric, but which has non-abelian gauge symmetry. I think that's good to stop.
Are there any questions for Henning?
Yes, what happens to the other higher P-forms in the hierarchy?
Well, as I said, in 4 dimensions, what happens if you switch on a generic gauging is, as we saw, you will have to introduce 2 forms to make things work. In 4 dimensions, the only way to introduce 2 forms without spoiling things is to introduce them in a topological way. So what will happen here is there will be some BF coupling, some new topological term in 4 dimensions. The higher forms don't even show up in the Lagrangian. Okay? In higher dimensions, if you're in 5 dimensions, more or less the same happens. The ungauged theory in 5 dimensions has only vectors. The moment you switch on gauged charges, you're bound to also introduce 2 forms. But these 2 forms, again, will come with a kind of topological term, B, dB. So the field equations will tell you that these 2 forms are, in fact, the duals to the vectors in 5 dimensions. And again, the 3 forms you don't see in the Lagrangian. From 6 dimensions on, you will also get the 3 forms entering in the Lagrangian. The structure is always the same. I mean, you have to add a few higher degree forms, but then it cuts off and you don't need all of them to.
Is the Bianchi identity satisfied for the
The Bianchi identity modifies, of course. In fact, well, in some sense, it's the only way it can. DF, now with the covariant, which used to be 0 before. Now, since we have modified the theory, all we know is this is a, sorry, with a curly f. all we know is this is a covariant object, this is a covariant derivative, so this must again be some covariant object. In fact, it is. It is just this tensor projecting the now covariant three-form field strength. Right, if I put here indices mu nu rho, this would be the three-form, this would be the field strength of the new two forms which we have added to the theory. Okay. And then Bianchi of this would go on and introduce higher order field strength and so on. So there is a Bianchi identity, but it's, so this is, there's a Bianchi identity, it's a relation between covariant expressions. Just now, it's also the two forms which show up in that